Covalent bond. A covalent bond is a bond formed by mutual sharing of valence electrons between two atoms. Look here at the hydrogen-formed covalent bond by sharing of each atom with single electron. On the basis of sharing of valence electrons, covalent bond is classified as single covalent bond, double covalent bond, and triple covalent bond. Single covalent bond. Let us explain the formation of Cl2 molecules. Each chlorine atom has 7 valence electrons. Each chlorine atom needs 1 electron to complete its octet. It gets a noble configuration by sharing of single unpaired electron between the two chlorine atoms. Thus, such type of bond is called a single covalent bond. A pair of electrons that is shared between two atoms is called a bond pair. A pair of electrons that is not shared between two atoms is called a lone pair. Double covalent bond. A double covalent bond is when two atoms share two pairs of electrons with each other. Let us take up the formation of oxygen molecules. In oxygen molecule, there are two oxygen atoms. Each oxygen atom has 6 valence electrons. So it needs 2 electrons to complete its noble configuration by mutual sharing of 2 electrons in oxygen atom. Thus, such type of bond is called double covalent bond. A triple bond is when 3 pairs of electrons are shared between the two atoms in a molecule. Let us take up the formation of nitrogen molecules. In N2, each nitrogen has 5 valence electrons in an atom. In order to attain an octet, each nitrogen atom in a molecule of nitrogen contributes 3 electrons, giving rise to 3 shared pairs of electrons. This is said to constitute a triple bond between the two atoms. Tetravalency of carbon. Let us understand that the carbon has tetravalency. Carbon has 4 electrons in its outermost shell and needs to gain or lose 4 electrons to attain a noble gas configuration. If it were to gain or lose electrons, it could gain 4 electrons forming C4 negative anion. But it would be difficult for the nucleus with 6 protons to hold on to 10 electrons, that is 4 extra electrons. It could lose 4 electrons forming C4 plus cation, but it would require a large amount of energy to remove 4 electrons, leaving behind a carbon cation with 6 protons in its nucleus, holding on to just 2 electrons. Carbon overcomes this problem by sharing its valence electrons with other atoms of the carbon or with the atoms of other elements. Thus, carbon has tetravalency. Let us understand it with the help of an example. Methane is also one of the simplest compounds formed by carbon. Methane has a formula CH4. Hydrogen, as you know, has a valency of 1. Carbon is a tetravalent because it has 4 valence electrons. In order to achieve noble gas configuration, carbon shares these electrons with 4 atoms of hydrogen to form methane molecule. Allotropy of carbon. An element in different forms having different physical properties but similar chemical properties is known as allotropy. Carbon has numerous allotropy and is classified as crystalline and amorphous. Crystalline are further classified as diamond, graphite and fullerenes. Amorphous is classified as coal, charcoal and lamp. Coal is the gas and petroleum products. Charcoal are further classified as wood charcoal, sugar charcoal and animal charcoal. In this module, we will just discuss the crystalline allotropy of carbon. Diamond. In a diamond, each carbon atom is joined to 4 other carbon atoms in a tetrahedral manner. 3 tetrahedral joined to form a puckered 6-member ring and capped by 4 tetrahedrals to form a large structure. Repetition of this structure to form a 3-dimensional structure is shown here. So, it is a covalent network solid, which are hardest substances. Graphite. In graphite, the carbon atoms are arranged in flat parallel layers as regular hexagons. Each carbon in these layers is bonded to 3 others by covalent bonds. Graphite thus acquires some double bond character. Each layer is bonded by adjacent layers by weak van der Waals forces. This allows each layer to slide over the other easily. Due to this type of structure, graphite is soft and slippery and can act as a lubricant. Fullerenes. Fullerenes form another class of carbon allotropes. The first one to be identified was C60, which has carbon atoms arranged in the shape of a football. It contains 5 rings membered and 6 ring membered of carbon atoms. Versatile nature of carbon. Carbon forms a large number of compounds because of 2 unique properties: tetravalency and catenation. Tetravalency of carbon. We know that atomic number of carbon is 6. Thus electronic configuration is 2, 4 and valence electrons is 4. Hence carbon needs 4 electrons to attain a noble gas configuration. Valency of carbon is 4. Due to this, carbon forms a large number of compounds with oxygen, hydrogen, nitrogen, sulfur, chlorine and many other elements, giving rise to compounds with specific properties which depend on the elements other than the carbon present in the molecule. Catenation. Carbon has the unique ability to form bonds with other atoms of carbon, giving rise to a large molecules. This property is called catenation. Look here. Each carbon joined together to form large molecules such as linear branched and cyclic structures as shown here. Lewis dotted structure of hydrocarbon. Let us draw the Lewis dotted structure of ethane. Let us now follow the steps. Write the electronic configuration of all the atoms present in the molecule. Carbon has 2, 4 and hydrogen has 1. Identify how many electrons are needed by each atom to attain a noble gas configuration. In the ethane, carbon needs 4 electrons while hydrogen needs 1 electron to a noble gas configuration. First, complete the noble gas configuration of all the hydrogen atoms by bonding each hydrogen atom with a carbon atom by a single bond. In ethane, 3 hydrogen atoms are shared with each carbon atom. The remaining valency satisfied by sharing of carbon atom to form single bond. This structure gives the Lewis dotted structure. Keep in mind that the shared electrons are counted in the valence shell of both the atoms sharing it. Let us take another example. In the ethylene molecule, 2 hydrogen atoms share single electron with each carbon atom, and both carbon atoms mutually share 2 electrons with each other. As a result, each hydrogen atom acquires 2 electrons in the outermost shell and achieves a noble gas configuration. Each carbon atom acquires 8 electrons and a noble configuration. Thus, carbon-carbon forms double bond, while carbon-hydrogen bond forms single bond. Classification of hydrocarbons. Hydrocarbons are classified as aliphatic or open chain hydrocarbon and cyclic or closed chain hydrocarbon. Aliphatic or open chain hydrocarbon is further classified into saturated and unsaturated hydrocarbon. Saturated hydrocarbon is further classified as alkane and unsaturated is classified as alkenes and alkynes depending on the carbon-carbon bond. Cyclic or closed chain hydrocarbon is further classified as alicyclic and aromatic hydrocarbon. Click on any one of the buttons to know more about it. Homologous series. A series of organic compounds in which every succeeding member differs from the previous one by CH2 or 14 unit mass. The molecular formula of all the members of a homologous series can be derived from a general formula. Homologous series of alkanes. General formula: CnH2n plus 2, where n is equal to number of carbon atoms. Look at the homologous series of alkanes, which are C2H6, C3H8, C4H10, C5H12, C6H14 and so on. Homologous series of alkenes. General formula: CnH2n, where n is the number of carbon atoms. Homologous series of alkenes are C2H4, C3H6, C4H8, C5H10, C6H12 and so on. Homologous series of alkynes are CnH2n minus 2, where n is the number of carbon atoms. Homologous series of alkynes are C2H2, C3H4, C4H6, C5H8 and C6H10 and so on. Properties of a homologous series. As the molecular mass increases in a series, physical properties of the compounds show a variation, but chemical properties, which are determined by a functional group, remain the same within a series. Isomerism. The compounds that can have the same molecular formula but different structures are called isomerism. Butane has two structures isomers, that are N-butane and isobutane. For example, in pentane C5H12, one can see a straight chain normal pentane, branch chain isopentane and a ring of cyclopentane CH5H10. 1-butene has the molecular formula C4H8. All possible structural isomers of 1-butene must have the molecular formula C4H8. The possible isomers of butane are 1-butene, 2-butene, 2-methylpropene and cyclobutane. Naming of hydrocarbon. Look at these compounds. Count the number of carbon atoms. There are 4 carbon atoms in the compound. It is symmetry carbon. Hence, both structures are correct. So it is named as but. It is a saturated carbon, hence suffix is ane. So it is named as butane. Look at other compounds. There are 4 carbons in the compound. Select the longest root chain. Start the count number of carbon atom from double bond in the given compound, which is lowest position carbon atom. So it is named as but. It is an unsaturated carbon, that is carbon-carbon double bond. Hence the suffix is ene. So it is named as butene. Look at other compounds. Start the count of carbon atom from triple bond in the given compound, which is lowest position carbon atom. Hence the suffix is ine. So it is named as butyne. Write the name of given compound. Select the longest root chain and others alkyl groups are substituents. The longest chain in the given hydrocarbon contains 5 carbon atoms and there are 2 methyl groups as substituents. The longest chain is numbered so that the substituent gets the least number. Here the chain is numbered from left to right so that the substituent gets the number 2. Then the hydrocarbon is named as locant number plus substituent plus parent chain name. Here 2, 2 is the locant indicating the position of substituent. Dimethyl is the substituent and pentane is the parent chain name with 5 carbon atoms. Hence the compound name is 2,2-dimethylpentane. If a hydrocarbon contains unsaturated bond, then the longest chain should contain the double or triple bond. Similarly, on numbering the chain, the unsaturated bond should have least number irrespective of the location of substituent. Thus the compound is named as 3-methyl-1-butene. Functional group. An atom or a group of atoms which when present in a compound gives specific properties to it regardless of the length and nature of the carbon chain is called a functional group. Let us look at some functional groups in a tabular form. Write the name of the given compound. Here compound has Cl and OH of functional groups and their position in a carbon chain. Word root is but, prefix word is 3-chloro and suffix is ol. Thus the name of compound is 3-chlorobutanol.
IUPAC name of chlorine compound. Let us write the IUPAC name of compound, that is CH3, CH2, CH2, Cl. Count the number of carbon atoms in the given compound, that is 3. So it is named as prop. Let attach the remaining atom in this compound. So it is a saturated compound. So add a suffix an in it, and that is propane. This compound contains one chlorine atom, so use the prefix as chloro. Thus the name of the compound is chloropropane. Combustion reaction. Most of the carbon compounds except diamond, like the hydrocarbons, when burnt in air or oxygen, produce large amount of heat, carbon dioxide and water vapor. Hence they are used as fuels. For example, methane burns with a blue flame in air. In a very limited supply of air, methane gives carbon black. Butane burns with air, also gives carbon dioxide, water, and a large amount of heat is released. Flame test. Saturated and unsaturated hydrocarbons. Let us do an activity. Take some carbon compounds, naphthalene and N-heptane, one by one on a spatula and burn them. Observe the nature of the flame and note whether smoke is produced. You will observe that naphthalene gives a yellow flame with lots of black smoke, while N-heptane gives a clean flame. Place a plate over the flame. A sooty deposits on plate in burning of naphthalene. From this activity we conclude that saturated hydrocarbons will generally give a clean flame, while unsaturated carbon compounds will give a yellow flame with lots of black smoke. Oxidation reaction. Let us do an activity. Take about 3 ml of ethanol in a test tube and warm it gently in a water bath. Add 5% solution of alkaline potassium permanganate drop by drop to this solution. You will observe that the purple color disappear on adding of potassium permanganate to the ethanol solution. On adding the potassium permanganate in excess, you notice that the color of potassium permanganate reappears in the solution of ethanol. From this activity, ethanol gets oxidized to give ethanoic acid in presence of alkaline potassium permanganate. Addition reaction. Unsaturated hydrocarbons add hydrogen in the presence of catalysts such as palladium or nickel to give saturated hydrocarbons. Substitution reaction. Saturated hydrocarbons are fairly unreactive and are inert in the presence of most reactants. However, in the presence of sunlight, chlorine is added to the hydrocarbons in a very fast reaction. Chlorine can replace the hydrogen atoms one by one. It is called the substitution reaction because one type of atom or a group of atoms takes the place of another. Ethanol. Chemical formula of ethanol is CH3CH2OH and common name is ethyl alcohol. Physical properties of ethanol. Ethanol is a colorless liquid with a pleasant smell and burning taste. It is soluble in water. Reaction of ethanol with sodium. Take a small amount of ethanol and add the sodium metal on it. What do you see? You see that the gases evolved in the reaction. Now bring a burning matchstick near it. It burns with an explosive sound. So this gas is hydrogen. Ethanol reacts with sodium to form sodium ethoxide and hydrogen. Reaction of ethanol with concentrate sulfuric acid. Ethanol reacts with hot concentrated H2SO4 to form ethene and water. Concentrated sulfuric acid is a dehydrating agent that removes water from ethanol. Ethanoic acid or acetic acid. The chemical formula of ethanoic acid is CH3COOH and its common name is acetic acid. Physical properties of ethanoic acid. Ethanoic acid is a colorless liquid with a pungent smell and a sour taste. It is soluble in water. A solution of 5% to 8% ethanoic acid in water is called vinegar. Is the acetic acid a weak acid? Let us check it. Take acetic acid and hydrochloric acid in test tubes. Dip the universal indicator in solution. You will find universal indicator gives light red in acetic acid and red color in hydrochloric acid. Thus pH of acetic acid is 2 to 3 and hydrochloric acid is 0 to 1. Reaction of ethanoic acid with carbonates and hydrogen carbonates. Let us do an activity. Take a spatula full of sodium carbonate in a test tube and add about 2 ml of dilute ethanoic acid. What do you observe? You will see that brick effervescence is formed. Pass this gas produced through freshly prepared lime water. This shows that evolution of carbon dioxide. Thus ethanoic acid reacts with sodium carbonates or sodium hydrogen carbonate to form sodium acetate, water and carbon dioxide. Esterification. Let us do an activity. Take 1 ml ethanol, absolute alcohol and 1 ml of glacial acetic acid along with a few drops of concentrated sulfuric acid in a test tube. Warm this content in a water bath for at least 5 minutes. Pour into a beaker containing 20 to 50 ml of water and smell the resulting mixture. Smell them. You will observe that a sweet smell is coming out from the solution. In this activity, ethanoic acid reacts with ethanol to form the ester ethyl ethanoate in the presence of concentrated sulfuric acid. Saponification. When an ester reacts with sodium hydroxide solution, the sodium salt of the carboxylic acid and the parent alcohol are formed. This reaction is called saponification. For example, ethyl ethanoate reacts with sodium hydroxide to form sodium acetate and ethanol. Soap. Soaps are the long-chain sodium or potassium salts of carboxylic acids. Example: sodium stearate, C17H35COONA. A soap molecule has two parts, that is, hydrocarbon part and ionic part. Structure of a soap molecule. It is a long hydrocarbon part which is hydrophobic or water repelling. Ionic part is made up of carboxylate ion of sodium or potassium and is hydrophilic or water attracting. Cleansing action of soap. When soap is dissolved in water and release large molecules of soap molecules, the hydrophobic N is soluble in dirt or oil, while hydrophilic N is soluble in water. When dirty cloth is added to a soap, the soap molecules are arranged such that the hydrocarbon part is towards the center and the ionic part is towards the outside. The hydrocarbon part dissolves in the dirt, oil and grease and forms cluster structure. This formation is called a micelle. Soap in the form of a micelle is able to clean since the oily dirt will be collected in the center of the micelle. The micelles stay in the solution as a colloid and will not come together to precipitate because of ion-ion repulsion. Thus, the dirt suspended in the micelles is also rinsed away. Detergents. Detergents are the long-chain sodium salts of sulfonic acids. Soap is used in soft water while detergent is used in hard water as well as soft. Let us do an activity. Take 2 test tubes with about 10 ml of hard water in each. Add 5 drops of soap solution to one and 5 drops of detergent solution to the other. Shake both test tubes for the same period. Do both the test tubes have the same amount of foam? In which test tube is a curdy solid formed? You will observe that more foam is formed in detergent solution and a white curdy precipitate in the soap solution. Thus, the soaps do not wash well with hard water because it forms insoluble precipitates of calcium and magnesium salts in hard water. Detergents wash well with hard water because it does not form insoluble precipitates of calcium and magnesium salts in hard water.